Farzi Yusuf Ali. I hope you've had a good start to your conference so far. This is a relatively technical talk, but I'll do my best to make it as digestible as possible. Today, especially given the audience, we'll be talking about improving the success rate of any mineral prospectivity you do, namely making your drill programs more successful using AI techniques. So, as you all know, exploration's generally a risky business. Therefore, any methods we can use today, especially those that come outside of the mining sector, should be utilized to make sure that we are able to supply our commodity needs for the next 20, 30 years as the easy to find, high-grade deposits become more and more difficult to find. So just as an overview, I won't touch on this for too long, but what Stratum does is we take whatever data a mine or a project already has, and we'll produce a better estimate of what's in the ground using non-geostatistical techniques. A little bit controversial, but hear me out. We will then use the data as is, raw data, namely collar survey assay data, to produce a prediction for a reserve estimate, increasing resources, or even going as far as improving mineral processing outcomes. The method is pretty simple. The analogy I'd like to use is like finding the snow in a mountaintop. So essentially what you have here are these features that you're trying to identify to see if you can find snow on any given picture. What you are then using is essentially a set of binoculars as you scan through the image to then pick out those features. That gives you an indication of what patterns indicate snow versus non-snow. That's a very easy way to understand the problem. Now, if we expand it to mining, you can think of it as taking a sample or a space, a land packet, and finding the attributes that would give you gold or no gold. So the way we test it is very simple. To make sure that we have a good model, we will take existing data or historical data and then predict into the future what the outcomes would look like. And we would repeat this process over and over again. You can split the data on a temporal way, so using time, meaning, let's say if I start from 2020 to 2022, I would use that data to train my machine learning model and then predict blind what would happen in 2023 and 2024. In more data-sparse environments, we can replicate that technique by using drill holes and going at depth. Furthermore, we can also split up the space regionally to see how our models perform across, let's say, if you're in one western-facing region, and see how it translates towards something as you go further east. Now, rather than talking about it in abstract terms, I'm actually going to use a case study and then pull out each of the concepts as we walk through an actual project. So this is the profile. Very famous mine, especially if you're from Australia. This is Jundee Mine, an orogenic lode deposit with a very high nugget factor, meaning that 40% of the time, whatever you measure as high grade is actually high grade. Therefore, finding actual mineralization versus nuggets is quite a challenge. And you can extend this to mineral prospectivity as well in some way, shape, or form. In any case, our goal here is to use the data that is available and find new areas to then add to the mine plan. We have to consider targets that are at least 6 meters away, therefore at least 12 times further than any given block size. And we'll also have to make sure that it is greater than the economic cutoff grade, which is about 2.2 grams per ton. Now, I'm going to start with the results, and then I'm going to work how we got to that point. So the results are, given any model predicting over 5 grams per ton, so definitely considered high-grade gold in this deposit, we were 24% more efficient in finding the same number of high-grade blocks than any existing baseline drill program that had been done up to about 5 years before when we came along. The second and more important thing is that in doing these exercises, we did not sacrifice adding more drill core to find more mineralization. we actually had a higher hit rate, meaning the precision of our models was much higher than what their own models were able to produce. So let's take a step back and now think about the techniques that we can use and you can apply to each of your own projects that would help you get similar results. Not perfect, but similar. So I'll break these out into 3 categories. One is using the data fully, meaning your geochemical assays. What geochemistry would end up being good pathfinders to finding your target element, let's say gold in this case. The second is, what lithologies can we use and can be diagnosed to then map it towards our geochem assays? Because as many of you all know, lithologies are as interpretive as any geologist that produces them. Therefore, tying it to any sort of data set that is measurable is quite valuable in this case when your data environments are quite sparse. And finally, how do we measure the quality of the resource model and the confidence of any drill target? And that's quite a difficult proposition, especially when you think about how do we measure the confidence of any resource model or any prediction that you make. So we'll start with the first line, and we'll talk about a geochemical ablation study that we did at Dundee. What we did was we actually grouped the elements that were being assayed across the entire deposit into its lithological categories, namely group A with hafnium being the group leader, paired with zircon, and then here, specifically group E, where we have vanadium being the group leader, which is usually tied to muscovite or roscolite here. You also have some cases where you have iron and scandium and copper also tying to your mafic material, but that's pretty standard stuff. Here, what we're looking for is elements that are not gold, but will help you find the gold. That's the general idea. So when we do an inspection, a correlation study, so to speak, we are not looking at linear correlations, because linear correlations does not add new data to or does not add new information to any prediction that you're making. What we're actually looking for here are nonlinear correlations. And these correlations, if I just summarize it for this particular case, we use 3 sets of correlation statistics. One is called Pearson, other one's called Spearman, and the third is called Kendall. Those 3 statistics actually allow us to create these correlation maps, which help us find zones that would be useful for predicting gold in this particular deposit. So you'll notice here, there's a nonlinear correlation of arsenic to gold, so high arsenic and high gold content. That's pretty standard, but you'll notice that what we're looking for is actually these values. If we're looking for the specific values and where that range actually lies, that is useful information as a pathfinder. In group E, specifically with vanadium, you'll notice that where there is high vanadium, gold does not occur. That is also useful information. So even though you're not necessarily finding gold, you're actually then finding the absence of gold, which will help you with your resource estimate. Same thing here in this particular scenario. Now, when we do this ablation study, we take every single element and then we match it against 2 different types of measurements. One is false positives, which can be simplified as when you predict high grade, how many instances of that is actually waste in reality? That's a false positive. So in that particular case, when we look at which elements actually help you find those instances of false positives, arsenic, scandium, beryllium, vanadium happen to be those elements. Now, in the opposite case, we're looking for mismineralization, a little bit easier to understand. In the event where you predict waste and you find high grade, is called mismineralization. We want to find those elements that would be pathfinders for those types of instances. So, as a result, we get this suite of elements. Now, mind you that these have been mapped to lithological codes that the mine has already produced. Therefore, there is some geological foundation to this type of analysis. And in reality, when we think about how we create our machine learning model, these inputs, these actually become inputs, separate inputs that would then be used to predict gold itself. Now we'll talk a little bit about ensembles, which is the third line, the third topic that gets you to this increased incidence of success for your drill programs. And it's a counterintuitive idea. Usually you assume that for any given model, you will throw as much data as you can in there and then produce the best result. In reality, that might not be the best tactic because not all data is created equal, not to mention that there could be error that could be permeating through and then causing your resource estimate to skew in the negative direction. So when we think about ensembles, we think of it as different viewpoints of the same target prediction. So let's say I'm standing here at the podium and I want to predict exactly what's being said in front of me. I'm closer, but I don't have a good vantage point. In another case, if I'm standing where the cameraman is, that is a perfect vantage point for this podium here. That is a completely different input environment compared to my input environment. And we treat these models the same way. So we're not necessarily creating one perfect model, we're actually using very disparate models to see which of those predictions happen to agree on a block-by-block basis. So in practice, we use a bunch of different techniques. So we talked about ensembles, so we'll take a step back again. Now that we've talked about these different viewpoints, we can now talk about different ways of parsing your own data as inputs. In this particular scenario, you can imagine that with these high-grade nugget values, you tend to also skew your grades down when you use things like kriging and normal compositing. However, by introducing a separate channel that takes the max grade of any composite, you actually retain that information where your high-grade value happens to be measured. So in this case, they used to use 5-meter composites. If in one of those meters, especially given a block size of 0.5 meter, you'd want to retain this information. So this is an actual input we could use into the model. Finally, we'll talk about the lithology, which would then cover section 2, or topic number 2 in this particular talk. How do we take lithologies, how do we group them, and how do we test whether this lithology is actually helpful for helping you find gold, or it's more of a red herring? So in this particular case, we chose very simple groupings. One is, are we able to tell the difference between country rock and unmineralized sulfide? That tells you whether there's a potential for gold or not. That is a very simple encoding of 0, 1, and 2, where you have 0 being country rock, MZ capable, which is unmineralized sulfur, and MZ, which is actually sulfur-hosted gold. Finally, we have a separate litho channel here, which allows us to take this mafic, felsic, and sedimentary rock into account. Now, the interesting thing here to note is that this is not used for domaining. This is used for inputs, direct inputs into the model. Finally, one litho channel that is not shown here is the presence of lampopheres. The lampophere class is actually very important to find, to use as pathfinders for gold, but we'll come to that in a second. So now, coming back to topic number 3, being the ensembles, you'll notice here that even though we had lampophere information, we had the different types of compositing, we had the different types of lithos, not every single type of information is included in every single model, because each one of them contributes something a little bit different to each other as far as what type of prediction it's making. It's the different vantage points. Therefore, if, let's say, 3 of the 4 models agree on, let's say, a certain prediction in block X, that is considered a high confidence prediction and should be used for targeting. And we'll get to some examples just now in a second. So these are some reconciliation against drill holes that were done in 2023. You'll notice that we, across the board, no matter what type of model we have, we perform better than the model that they were using for their drill programs essentially. There's 3 different reasons for this type of improved estimate. One is machine learning over kriging, which we can talk about later. But more importantly, it's the use of these lithos and these litho groupings that are actually more valuable in finding gold. Because segmenting your lithos into its very detailed categories actually introduces more problems than it solves. So by grouping them, you just get a general idea of where the mineralization happens to be going without introducing that type of interpretation area that you tend to see with this type of estimation. And finally, most importantly, combining those models with those disparate inputs actually allows you to then produce one estimate or one prediction per block that is extremely high confidence. Therefore, when you're measuring it against the truth, let's say data that's collected in the future in 2024 or any drill program that I would execute, this would be the results I would expect. And now let's look at the converse case. The converse case is, let's say I have a great drill program and it's giving me lots of high confidence predictions. That doesn't necessarily mean that my model is precise. I could literally put a drill hole anywhere and call it high confidence. What I'm now looking for here is, can I efficiently put these holes down to ensure that I'm not wasting money every time I'm looking for high grade? So between this graph and this graph, you'll get a full picture as to how confident or how performative your models can be for drill programs specifically. So now what we get at the end is something called probability volumes. So given some number of blocks, we can actually assign a probability to them. So given a selection of ensemble models, let's say 10 to make the math really easy, if, let's say, a chunk of them tend to agree in a certain type of prediction, that is a high confidence prediction in high grade. And we can actually count the number of blocks we have that fulfill that condition. So you'll notice here that especially for such a large mine, 38% of all the drill holes that were drilled out found that the probability was above 10%, especially for this type of exploration program. That is extremely high in terms of that's an extremely high number in terms of our probability scale for what we expect to come out of the ground. This is even more true for anything above 5%. That means that these methods can be used for more risky drill programs where you're truly moving into unclassified regions or inferred regions, and you're trying to essentially create a better reserve estimate. So this is probably the best picture and gives a very good idea of what we've now built. So here you'll notice ensemble 1 with high Lampefehr weight, meaning those pathfinders, and low Lampefehr weight. What you'll notice here is because of the ensembles that we've created, we're actually able to create a probabilistic cloud or a map of where those targets should be. So you'll notice that here and here, those targets do actually do match each other despite the lower Lampefehr weight. And then we can also compare that to what kriging produced. So you'll notice there's some differences here, where kriging does not predict those high grade areas. So this, as a result, by using these methods and not necessarily putting all of that data together into one model, what you're able to create is this probability map, so to speak, which is directly related to how well each of the separate models agree with each other for any given prediction. So now let's actually look at some drilling that was done. You'll notice this is the before. This is an example drill target. These are some historical holes. Whoops. These were some historical holes that were put in. And here are some actual holes that were put down based on our directions. So you'll notice we actually hit this gold vein here that was missed. And what we then plotted was the Lampefers as those pathfinders. What we then noticed was that just by using this qualitative information, that showed us that our drill programs actually work and that Lampefers are good pathfinders, whether we conduct those drill programs or the mine does themselves. Now here's another case. This is more for resource definition, but it shows sort of how we use this type of drilling to convert very, very efficiently from anything that's indicated lower risk to higher risk, essentially adding it to your reserve estimate. So you'll notice that from before to after, we are able to move to 70% confirmed with just, I think, 1, 2, 3 holes in this case. 1, 2, and 3. Now, this is the blue sky target, which is probably more interesting. This is where this entire region is unclassified. This is infrastructure. We just put 2 holes in the ground that targeted the highest grade material we could possibly find. So here, in this purple area and this blue area would be high grade gold. Well, you'll notice that all of this material was unclassified. By using this method, we are able to project past the data boundaries and find these targets in this manner. So these are the results. We've gone over them a little bit. I won't go over them again. But what I'll note here is that by thinking about it from both a precision and a recall standpoint, namely false positive and mismineralization standpoint, you get a better idea of how well your models are performing in terms of your drill programs. Therefore, even though we found 3.2 times more material than any baseline drill programs they conducted in years past, we're still able to reduce their drilling costs by 24%. Next, I think because we have a little bit of time, I'll show you one more, which will show you some expansion type drilling, which also moves a lot of unclassified material into measured material. So this now is an IOCG copper asset in Chile. 120K geochemical samples within the asset, but then literally nothing north and south of the main manto. So we're exploring into the breccias in this case. So this is the summary. We targeted these zones here, 6, 16, and 65. Note that this land packet did not belong to them at that time. Only this did. This part of the infrastructure was theirs, and this part was also a land packet that they did not have. Using our technology, we not only noticed that there was nothing to be explored in the south region, and we ended up then directing their efforts north. Here, their belief was that there was a hard fault here that actually stopped the mineralization directly. Our analysis proved that actually what had happened was a very large shear had occurred in this zone, therefore it should be worth exploring. So not only did we find things in the infrastructure, but here I think is where it was most interesting. This was undrilled at the time. So as a result, we actually ended up with those 3 clusters alone. We found $64 million in situ value. Average grade was about 1.5% copper, which is about 3 times the cutoff grade. So I'll quickly go over those 3 concepts just so that we can have some learnings to take away from this. In this particular case, their geochemical assays had a lot to be desired. They only had copper and gold. So even though copper and gold are linearly correlated, gold did not add unique information to finding more copper or more high-grade copper. Therefore, it could not be used in this case. However, in their logging, we noticed a lot of material that was visually logged but never assayed. And what we noticed as well was that 40% of the time, that material that was logged as country rock was actually low-grade copper. So we had to prioritize that data effectively and introduce it as a separate input such that we still learn something but don't introduce too much of that error that comes with that type of data. So we talked about ensembles. So here, again, we have a set of ensembles as well. So you'll notice there's some logging that we added, namely just manto, breccia, or manto plus breccia, very simple groupings. In this particular case, I'll note the ZFC, which is the visually logged material that we added as a separate input channel. And here we're combining the average composite and max composite, those concepts that we learned last time. Now here's the target, the target in the north. In this particular case, we actually found 55 meters of 0.63 copper grade, and then some outlier grades here, as you'll notice, 2.3% and so on and so forth. And then some more. So we put 5 holes in total in this particular area. The intercepts are shown here. But here's the important thing to note. Before the estimate, there was no estimate, truly. The actual percentage of high-grade volume was 36%. We found to be 36.2% of that material to be high grade. The average grade was 3 times higher than the cutoff grade, and the approximate value of this, just this cluster alone, is about $26 million in situ. So, with that said, given the activity around mineral prospectivity and the fact that these data environments can be so sparse, it is important to be able to leverage your data appropriately so that you're not introducing some of that error that comes in when you take everything and dump it into one model. By separating that data, allocating in its proper prioritization allows you to get these types of results, because then you're only taking what's exactly useful to you and not introducing more errors as a result. Any questions? I think we have a little bit of time. There's one.
First of all, thank you for the great presentation. I just want to ask about the ensemble machine learning. What kind of algorithm you used, and what the effect of the hyperparameter you changed to the results you have?
So the algorithms we use are deep learning algorithms, so convolutional neural networks. However, these are not like the off-the-shelf CNNs that you see today. So CNNs, convolutional neural networks, will look a lot like the LLMs, ChatGPTs that you see today. Ours do not look like that. So just take that with a grain of salt. So our convolutional neural networks are a little bit different because mining in and of itself is the data setting is also a little bit different. Therefore, that work is proprietary, so we'll leave that aside. The hyperparameter tuning, it has is distinctly important specifically for tuning the recall, the false positives, and the mismineralizations we talked about. Let's say, for example, I was dealing with an underground system and I wanted to think about stope optimization versus drilling. I would want a more constrained model. Therefore, I would not allow my model to have too much false positives, because then I cannot construct my stopes correctly. So those hyperparameters that you tune will tell you where you're going to, how unconstrained your model actually ends up becoming.
And the effects of that on the results, did you see any different results when you change the hyperparameter?
Yeah, so if we change the hyperparameters in this particular case to be, let's say, more precision heavy, we find that our models become more constrained. So we cannot predict, we can only really predict within inferred and indicated regions. We cannot go past the data itself, or the data frame itself. So it's just harder to extrapolate to unclassified regions because there's less confidence between, or less confluence between all of the individual models, because our threshold becomes higher. So let's say for stope optimization, here in this case we saw P greater than 10% as probability. That's okay for drilling because you're okay with missing some holes. In stope optimization, if I took that P value, it would be closer to 40-50%. That's why the differences matter.
What about other algorithms like random forest and extreme gradient boosting? Did you try this?
Yeah, we tried those algorithms. They were not able, long story short, they do not capture the complexity of any geological pattern to a level that is better than kriging. You get stuck with clustering and you get stuck with just linear types of correlations, especially when you come to random forest, because you're still stuck with linear correlations. You're not going truly nonlinear in your analyses. And there's I'll put it this way. You have a linear equation, a system one linear equation that dictates, let's say, some geological event, let's say a hydrothermal event. That's one linear equation. Then you have an alteration that happened on top of that. Then maybe there were some structural shears. So that's now a system of linear equations. When you look at random forest, it'll look at those linear equations separately, but they will not introduce dependencies between each other. However, with machine learning, you can introduce those dependencies. That's the easiest way I can explain it.
Okay, thank you.
Any other questions? No? Thank you so much for listening. By all means, find me, I don't know what my booth name is, but find me in the link next to the Hub of Excellence.